Hey Geometry, welcome to our probability unit. This one's a bit of a weird one, kind of heads out in a different direction, but it's something that we've got to cover in this class. So yeah, happy to be doing it with you here. This first section is a lot about vocabulary, so yeah, let's just dive right in. So an experiment, you may have an idea of what that is, but in probability, we call an experiment any action, so an action or trial where they're varying with varying results. So things like rolling a die. So an action or trial with varying results. You know, something where the result is unpredictable. That's when we're talking about with an experiment. That is rolling a die, as an example, or flipping a coin, or drawing a card, all that classic stuff, or something like dropping your phone. You could think of that as an experiment, and the results would be, does it break or not? And it's, you know, you may or may not know the results of that experiment. So outcomes is a possible result from the experiment. Possible result from the experiment. So to follow with our previous example, a possible result from rolling a die is that you get a 2. When you roll it, that's one of the possible results. The sample space is the set of all possible results. So in this case, we do sets. When we do set notation, you do this little bracket. That's a common way to do it. And then things separated by commas. So when you roll a die, 1, 2, 3, 4, 5, and 6 that is the set of all possible results as a result of rolling a die. All right, so one tool that we're going to use in this section that can be helpful is a tree diagram. We use a couple of different visual aids, but a tree diagram is a very useful way of finding the sample space when there are multiple actions. Draw a tree diagram, then list the sample space and determine the number of outcomes for each scenario. So first picking a digit 1 to 8, so and then tossing a coin. So we draw a tree diagram, 2, 3, 4, 6, 7, 8. So we pick a digit 1, 2, 3, 4, 5, 6, 7, 8. So that's kind of our first branch of the tree. And then off of that, we toss a coin. So after each of these, there's another branch, another split with 2 possible outcomes. We could get heads or tails, heads or tails, heads or tails, and so on. And so if you look down the branches, you can see all the possible outcomes. So we could get, if we did those things, a 1 and heads. And so that would be one possible outcome in our sample space, 1 and heads. We could get 1 tails, and then we could get 2 and heads. And we could get 2 and tails. And so then I'll continue on and fill that in. And then also we can think about the number of possible outcomes. So each of these is a unique outcome: 1 heads, 1 tails, 2 heads, 2 tails, and so on and so forth. So if we count those all up, we see that we have, we can count kind of just the end branches here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes. And so let me pause and get the rest of these in. All right, so there we go. There's our listed sample space of all 16 possible outcomes using that tree diagram. All right, the next one. How about randomly guessing the answers to the last 3 multiple choice questions of a test if there are 4 options for each question? So your first guess, and so we could do our tree diagram vertically. We could also do it horizontally. I'll do it this way just to show another possible way of drawing one of these out. So we could choose A, B, C, or D. We're just kind of counting possible outcomes, defining the sample space. So there, and then we have 4 choices off of that: A, B, C, D. And then this is going to get kind of messy. Maybe I should have gone the other way with this. 1, 2, 3, 4. A, B, C, D. And then A, B, C, D. And I'm going to put branches on each one of these. I'm not going to fill them all in, but you can kind of imagine how this would look. A, B, C, D off of that one. A, B, C, D off of this one. I'm not going to be able to fit this in, and so on. We would repeat that process going on down. So let me start to look at calculating what are all these possible outcomes that we could have in our sample space. All right, so this one gets pretty nuts with how many possibilities, and this kind of shows you, well, we'll need another rule for this, but we had 4 branches here, 4 choices we could have for the first one, 4 choices for the next, and 4 choices for the last. And so we have AAA is one possible branch. So if you can see, I go down this A to this tiny A to B is another one, AAC is another one, AAD, and then we can go on to AB, AB, B, and so on, ABC, ABD, and then we could go on to ACA, ACB, and so on and so forth. So it goes on and on and on. And so how many possible outcomes are there for that? That gets to be too much to kind of draw out already. Just 3 multiple choice questions. If you just guess on 3 multiple choice questions with 4 options. So what we can start to think about is another rule for coming up with this. And we'll cover this multiplication rule in a second, where we have 4 branches here. And then if I branch off of each of those 4, now I'm up to 16 possible settings there. And if I take each of those 16s and I split them into 4, that's 4 times 16. So it's really 4 times 4 times 4. So if we do that 4 times 4 times 4, or 4 cubed, we're going to have 64 branches. And I just don't have enough space to write all those. But there are actually 64 possible outcomes in that setting. So already there, quite a bit to draw, too many to list, 64 possibilities. That's just 3 questions. If I do another question, 4 more times that, 256, and then it gets nuts really quick. This grows exponentially. All right, one more example here. You can try and do this one on your own first, or follow along. This one's a little bit different. Choosing a day of the week, then choosing a letter from the word math. So our first choice, I'll go back to branching this way because I have a little more room this way. 3, 4, 5, 6, 7 possibilities. So we've got Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday for a day of the week. And then off of each of those, 4 branches. So you can already think about how many possibilities we have. If we have 7 splits on the first, and then each of those has 4 branches after that, so it would be 7 times 4. That's going to be 28 branches. We can count them out: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So, and then you guys can hopefully see that sometimes you don't even have to draw a complete tree diagram to help you think about a problem. You can even just kind of start to draw it to help yourself kind of visualize what's going on. I will finish this one out though. So M-A-T-H, M-A-T-H, and so on. And there are 28 possibilities to list, so I'll list several of them. Not all of them, because 28 is a little bit too much to fit into that box. But so our sample space, if we start that out, we could have Sunday and M. We could have Sunday A. We could have Sunday T. And we could have Sunday, I'm abbreviating that, H. And we could have Monday M. And Monday A. And Monday T, and so on and so forth, all the way up to Saturday H, would be our last one. Saturday H would be the last of the 28 that is in the entire sample space. So can draw it out with a tree diagram if we take our time. Even this one over here on this page, we could have drawn it out, but it takes some time. All right, and then so next we have the fundamental counting principle. And so this is kind of what I was just talking about. You can use the counting principle to find the total number of outcomes. If one activity can occur in M ways and another activity can occur in N ways, then both activities can occur in M times N ways. We can multiply that out to get the number of outcomes. So Some examples of this: choosing a month of the year and a digit 1 to 9. So that would be 12 ways for the first. And then digits 1 to 9, that is 9 digits. So 12 times 9 gives us 108 possible outcomes. Choosing a letter of the alphabet, 26 choices. Then tossing a coin, so 2 options, 2 sides of a coin. 26 times 2 gives us 52 possible outcomes. All right. Choosing a pair of pants, a shirt, and a belt from 3 pairs of pants, 5 shirts, and 2 belts. So this rule actually goes beyond just 2 things. So I have pants, which I have 3 choices, so 3 choices. And then if I just did pants and shirts, I have 5 choices, so that would give me 15 choices for pants and shirts. Then if I have 2 more belts that I can throw into that, we can just continue on, take those 15 possibilities times 2 possibilities, and get the grand total of 30 possible outfits in that setting. So it can go beyond just the 2. You can kind of do the first 2, and then add on a third, and then on a fourth, and however many. Rolling a standard die 4 times, so a standard 6-sided die, so 6 times 6 times 6 times 6 is, and that one works out to be 1,296 possible outcomes of just 4 die rolls. You could get a 1, a 1, a 1 and a 2, a 1, a 1, a 3 and a 5, a 1, a 5, whatever. 1,296 of those. Choosing one student from a class of 32 students and another student from a class of 27 students. So that's just 32 choices times 27. And that works out to be 864 if you multiply that out. And you can try and get ahead of me, pause, get ahead, and see how you do. Spinning the spinner to the left 3 times. So looking over at this spinner, we've got 1 through 16, so 16 possibilities. We want to make sure we assume that this is a fair spinner and not some spinner where certain regions are bigger than others. It seems to be a fair spinner, so we're going to go with a 1/16th chance for all those. I guess. So I'm thinking probability. Even outcomes, it doesn't matter if they're the same size, but I'm thinking probability, thinking ahead. Just counting outcomes, yeah, there's 16 possibilities, 3 times. 16 times 16 times 16, which works out to be 4,096. Tossing a coin 5 times, so there are 2 outcomes, times 2, times 2, times 2, times 2. All right, that one might be sped up nicely by doing 2 to the 5th. If you are repeating, that can be nice. Ends up being 32 possible outcomes. Creating a 4-digit password from the digits 0 through 9. Be careful with this. 0 through 9 is actually 10 digits because you're counting the 0 as one of the 10. So you have 10 choices times 10 times 10 times 10, which gives us 1 with 4 zeros after it, 10,000 possibilities for a 4-digit PIN. Choosing a perfect square number that is less than 50, then a letter from the word signature. All right, so this is where it just gets kind of tricky when you combine these together. Perfect squares less than 50, so those would be 1, and I'm just going to have to go through. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, sneaking under there. What was that? 7. 8 squared is 64. No, that's too much. All right, so I've got 1, 2, 3, 4, 5, 6, 7 for my first possibility. That was already just some math just to figure that out. And then a letter from the word signature. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 possibilities. So 7 times 9 gives us 63 possible outcomes from that one.